comprehensive today the HOD meeting is there. After 2 days after that, I can say whether this will be done, it will be shifted, or what will be the mode of all those things. Today you have HOD meetings in the institute.
So now live
tomorrow
on
I can tell you.
YouTube.
কি খুললে टे मुंह पर देखे बताओ ना तिमिद द वरुण हाँ କିଛି नहीं होने आपको हाँ तभी जो अच्छा आपको ଆସିବେ हाँ को फोन लगुनि हाँ कौन करिवो
सर नमस्कार
तमे आसिलोनी केबेटु आसिलो
सर ते
और
कथा
केबेटु
होउछ
आसिलो
सर सर कथा होउछ
16 डिसेंबर आसिलोनी अच्छा तुम केते पिला आछन तुम सी एस आबेल आसी तुम अन्य एमएस पिला आछन तुम तो इंटीग्रेट दि जण आछो आउ ये वाला आछन 2 इयर्स वाला के आछन सब आछन अच्छा तुम ये सब क्वारंटाइन पर सरी जान तो 16 रे आछन सरीबनी हाँ को कौन हला को बागन जीव हाँ कौन कौन लिख ओ जीव परमिशन तब लिखि दो ना मुझे तो देखि देबो नहीं कि लिखे तो नहीं ही मे भी परमिट लिखि देबे
सर कॉल आसी
कौन काम अछि
अरे फोन कॉल आसी काटी दवा तो
हाँ हाँ
स्टार्ट
so
करियो
now we can start the webinar over to
So
Umesh sir
let me see after actually I am in a seminar. I'll talk to you. I'll talk to you.
over to Umesh sir
Honorable Principal Sir, I request your honor to grasp the chair of President of the webinar on today and inaugurate the meeting. Principal Sir.
Good morning to everybody who
थोड़ा
are
बाद में करेंगे अभी सेमिनार में
taking
हैं।
part in the webinar organized by Department of Physics. In this auspicious occasion, we have with us Dr. Dhruvananda Behra, Assistant Professor, NIT Raulkela, as our Chief Speaker, as well as Chief Guest.
कोडी कोटिया लग रहे
I welcome you, sir, on behalf of our institution and department. I'd like to request all the members who have taken part in this webinar
ना सुने गई रे
and
Asuni.
असले
yes,
it has come
hello,
okay fine
Sir asila to?
no it's okay fine can you listen to
Ashok
me
sir please continue sir
okay
so
fine
I will request Head of the Department of Physics, Professor Umakanta Sahu, to give the introduction of the guest and to continue the webinar. Thank you. Over to Umakanta sir.
Thank you, sir. Warm reception to all of you in the digital decorated platform. Respected President of the webinar, esteemed chief guest of this harmonic occasion, academician from the different colleges of the state, faculties, participants, and my dear students. I, on behalf of the Department of Physics, warmly welcome our chief guest and chief speaker, Professor Dr. Dhruvananda Behera, HOD, Physics and Astronomy, NIT Rourkela, to the one-day national webinar on fundamentals of superconductivity, organized under the aegis of Department of Physics. In the present scenario of the age of evolution of science and technology, this topic will stand as a ray of hope for the welfare of the mankind as well as the academic and scientific fraternity. Professor Daiter Rao is a man of physics with profound knowledge, sincere, honest, dedicated man in every respect. I am proud to get the opportunity to avail this personality on the webinar. Then I request Mr. Latanu Mahapatra, lecturer of our department, to deliver keynotes on the topic.
Pranam sir.
नमस्कार
Respected President of this webinar, Professor Daitari sir, and Principal of this college, esteemed guests, come chief speaker of Professor Dr. Dhruvanand sir, head of the Department of the Physics and Astronomy, NET Raulkela. The HOD of the Physics Department, SG College, Professor Uman sir, and organizer Professor Pradeep sir. All the heads and faculties and other participants and my dear loving students. I am very exciting because I am going to introduce there is a webinar on my physics department on fundamental of superconductivity. Nowadays, superconductivity is play a vital role all around the world in the material science because it has no resistance to the circuit when it below a certain temperature. And there is a discussion on the development of superconducting material and some experimental perspectives such as Meissner effect and isotopic effect, and some theoretical survey will also be discussed such as London effect BCS theory. Finally, some research oriented conclusions are there. So we heartily welcome to our esteemed chief guest to share some moment with us to discuss superconductivity. Welcome, sir.
Umesh sir, please. Hello. Umesh sir, please unmute yourself and speak, please.
Mute. Unmute करो.
Sir.
Okay.
I request Dr. Professor Dhruvananda Behera to deliver the speech.
Okay. Shall I start now?
Sure.
Okay, fine. So now I welcome all of you to this topic that we are going to discuss. This is the request of Lolaten that they are organizing this seminar in their department. So I gladly accept this because for these things we are working more than we can say called 2 decades, right? So along with the superconductivity, some of my students also working on magnetism like ferrites, and some of the students already work out on this project of superconductivity. Today, if you see, then I will not discuss this difficult part of the research, but I can student can be encouraged to do work on this field of superconductivity. So I will only touch upon these fundamentals of superconductivity. That means very understanding for the, even if this school student and even if +2, +3 level, because as I know that most of the students should be benefited of your college, and I know that most of these known people are here in your department. So I think they will make some interest, and the student will be encouraged. They can be have this motivated to do some fundamental work on this work like superconductivity. So from the beginning that you see here, once again, before starting of the seminar, I wish you a happy new year, all of people, because this is initially we have started the first week of the new year, and we hope this year will bring you a very healthy life and avoid you all this unsafe life of 2020. So let me start then. I once again thanks all the people for calling me, inviting me for this seminar to have share with some of these things which I have learned during this long time of activity. So now I am going to share this thing that you see here. Let me see where my slide is. I want to share those things. So Is it audible and also
Yes,
visible
sir.
to you?
Yes, sir.
Yes, sir. It is
Right,
clearly.
fine. Thank you. Now let me start the topic that we are basically discuss for the coming maybe 1 year. So in 1 hour. So now this topic that you see, I have already mentioned that I will not go detail of those things. I will make you understand those things, and people may be interested. This is known as fundamental of superconductivity, right? And what the superconductivity shows that basically the material has a superconducting capacity. This is the plan of presentation of these things that you see here. The understanding of the phase transition, because superconducting shows a phase transition. That means when some materials are cooled to certain temperature, which is called as the transition temperature, so naturally you can have a phase transition. So now let us understand this phase transition. Then we'll discuss the conductivity in the materials and superconductor, because most of our students are doing this the conductivity, because the maybe electrical or maybe magnetic, whatever may be the conductivity system, thermal conductivity, whatever may be. Then come to understanding of superconductivity, types of superconductors, different phenomena for its understanding, because when you say understanding, this can be understood with different phenomena, different experiment, different ways. Then as you see that if you have a material characteristics, all those things, it must have an application point of view toward the society, maybe to this human race, or maybe to this basic understanding. Then if time permits and you permit me, then I can give the work that we have carried out in our department, particularly my laboratory. Then I'll give you the conclusion.
Yes, sir.
When I talk the phase transition, right, then you know that when you talk a phase transition, that you see matter shows a phase transition, right? That means matter changes phase with the different external parameter. The internal parameter also changes, like energy in a system. And we have the idea of phase change, like solid, liquid, gas, and plasma, the fourth state of matter, right? So for your understanding, I am not discuss you when you looking at this low temperature, because we are working low temperature. Now we have a fifth state of matter. I will touch upon, and these things, what is the fifth state of matter, particularly when we are working with low temperature. And these are this with the enthalpy of the system. The basically enthalpy means analogous to temperature. We know this very fundamental idea from the beginning of our learning, that we can have solid, liquid, gas, and plasma. So now starting with solid comes to a liquid by melting, and liquid can come to solid by freezing. So these are known as freezing and melting temperature of those things. Similarly, liquid can go to gas by process of vaporization, and gas can come to liquid by process of condensation. Similarly, gas can come to solid by process of deposition, or solid can go to gas directly by process of sublimation. These things from our childhood we know these are the phase transition, and these are basically first order phase transition. Similarly, gas can go to plasma, because the plasma state, by process of ionization. Similarly, the plasma can come to gaseous state by process of deionization. These are the very fundamental things that we have understanding from the beginning of our learning. Now, what I mentioned here, that these things that you see here, that related to one important parameter we call order parameter. This order parameter happens to be, for this type of behavior, the first order phase transition, we call this the density of the state, density of the matter. Like solid, liquid, gas, and plasma, they have different density. So this density is known as order parameter of these things. And this was a first order phase transition. With the first order, second order phase transition that you see discussed, then you have a long way of discussing. So I will not go detail of those first order, second order, but you see, we have a second phase transition. You can learn something of second transition, that when a magnetic phase transition a ferromagnetic substance can't go to a paramagnetic substance. By process of heating, we call transition temperature, we call Curie temperature. That is the secondary phase transition, because you do not sense a change of this density like behavior. But the second order parameter give rise to magnetization. Basically, that is the second order phase transition. I will not go detail of those things because we have many things to learn. So this will give you the idea that what basically a first order and second order phase transition. Look at because these were related to our superconductivity. Now these things also you can have that when you have pressure and temperature related to these phase change, you can have a gaseous phase, you can have a liquid phase, you can have the solid phase depending upon the pressure and temperature, and you can try critical point, like critical point that you see here. This can liquid, then you can have the superheated vapor phase, and you can have compressible liquid, then you can have solid, and this time you can have supercritical fluid. That means this phase that you see here can be have critical points. Looking at the pressure, they can be have a different phase of the solid, liquid, and gas. Now, coming to the second aspect that we have already mentioned in your proposal, we call this conductivity. And this is very fundamental thing that the classical model, which is known called as Drude model. What do you mean by the classical model? So Drude model, basically the conductivity that you see here, Drude has developed this theory by considering that matter as a classical gas of electrons, okay, governed by Maxwell-Boltzmann statistics. This is the statistical that you see here. This is known as Boltzmann and Maxwell-Boltzmann statistics. Particularly, this is electron for obeying this the Maxwell relation, because this has gas of electron, because this mini matter, these electrons are loosely bound. So generally we call the gaseous electron, because these are conducting electrons, and we call particularly C of electron, Fermi electrons, because they are Fermi gas, because they are loosely bound to the system, right? And the relation that you see here, the Fermi-Dirac Maxwell-Boltzmann statistics can be go by e to the power exponential Weber minus energy divided by K beta T. K beta the Boltzmann constant, T is the absolute temperature. That means you see this type of the kinetic theory of a gas to conduction electron, even though, because you how to apply these things, even though the electron densities are 1,000 times greater, because looking at the gas and the matter that you see here. So we call this gaseous electron, because in though the system is metal, we call Fermi electrons. What are the assumptions of the Drude model, the classical model? Ions are arranged in a fixed position and cannot move. Collision between electron-electron, because electron-electron collision is not taken care of here, because you see the collision between electron ions are instantaneous on correlated event. They are not correlated events also. Drude model. Ignore all interaction. You look at these things, the assumption of Drude. It's ignore all interactions and independent of electron aspiration or free electron aspiration. Look at those things. This only takes the free electron, ignore all these interactions. Then electron experience a collision with a probability per unit time. Basically, tau is the mean time between collisions, and 1/t related to time factor that you see here. Tau is independent of electron position and movement. This is a very fundamental assumption of the Drude, which give you the conductivity of the metal. Now, a simple way that we are going to discuss the superconductivity, let us have some idea of the metallic and insulator. Look at these things as we discuss this electron. Look at the metal and look at the electrons. As I mentioned, the electrons are tightly bound to the new insulators. Look at the left side, and the right side is insulator, left side is metal. So the metals, the carriers are the electrons. Okay, look at the red color that you see here. These are almost free in the matrix of the positive ion. Look at the positive ion cores. Whereas in the system that you see in the insulator, the electrons are tightly bound to the nucleus. So for that, this region, there is no free electrons in insulator. So that has a resistivity is very, very high. Look at these things that you see left and right. Now you can see the behavior of the material. You can have now have the superconductivity, what you call it. We'll discuss more detail in next slide. You look at the left panel that you see here. The scattering electrons by the process of collision, ions and electrons, right? This is a simple way that we discussed previously. And the right panel that will particularly give you the behavior of a normal metal. Look at those things. And a superconductor that you see here at particular temperature, the metal which behave as superconductor at particular temperature, resistance drops to 0. And that temperature we call transition temperature. This is behavior of superconductor in response to electrical resistivity and temperature. Now, naturally, what is the this electrical resistivity? Because you are conducting the resistivity of the material. And you know that current density J is equal to this relation that I am not going to derive those things because no time is there, because we know this also. The current density is J is equal to NeV. N is the number of electron, E is the charge of the electron, V is the velocity. You can call it a drift velocity also. Velocity inside the system, in the crystal. So this velocity that you see, we call drift velocity, is equal to, can be written as E tau by M, and E the electric field. So you look at this thing from here, you can say, you know this Ohm's law, the fundamental law of resistivity or electrical conductivity. That is Ohm's law. J is equal to Ne square tau by M and E. So if you look at those things, Ohm's law, J is equal to sigma E. Natural sigma is the conductivity that can related to J is equal to Ne square tau by M. This is very fundamental understanding looking at the Drude model. What is there you see? Current is caused by electric field. Current predicts linearly, or you can say it depends also. Current depend upon linearly on the strength of the electric field. Current density that you see J depend on the conductivity of the material. These things you know. And when you know the conductivity, then resistivity nothing but the reciprocal of conductivity. Rho is equal to 1 by sigma, that is equal to M divided by Ne square tau. This is our fundamental understanding of the matter, and from where you can have the superconductors. Now let us see what basically we understand by superconductors. Superconductors are the materials having almost zero resistivity, almost no zero, almost zero resistivity, and behave as diamagnetic behavior, right? And it has a below this superconducting transition temperature Tc. Okay, that means superconductivity is flow of electric current without resistance. Basically, we call R is equal to 0, but still some resistance there, very low, 10 to the power minus 12 or 15 ohm. That means superconductivity is the flow of current without resistance in certain metals, alloys, even if the ceramic also, at temperature near absolute 0, right? And in some cases, the temperature that you see here, basically, it can be this. What are the Tc value of these things? I will show you. Particularly when talk about absolute 0, then absolute we call it as minus 270 degree Kelvin, right? That means these under the different Kelvin temperature, you have the transition temperature. Look at those things. The first things that particularly we have superconducting material, resistance of mercury falls suddenly below accuracy. Measurement, we see that how you look at the behavior, that when you tell R is equal to 0, still then you say 10 to the power minus ohm. Okay, that means this is the transition of mercury 4.2 K. So this is the beginning of the things which has been discovered in 1911 by Kamerlingh Onnes. Now you look at these things, as I mentioned those things. Superconductivity is an exciting field of physics. Look at this behavior, we call this type of behavior, we call masonry effect. Look at those things. That means below is a material and it becomes a superconductor. When it becomes superconductor, if you put a magnet on top of it, it cannot touch. Why? Because it has a diamagnetic behavior. The superconducting material develops a magnetic field, and this magnetic field does not allow the other magnetic lines of poles to penetrate. That effect known as masonry effect. Look at the masonry effect that we see. Okay, so and see that this type of behavior is known as levitation. I will give you idea what basically the usefulness of levitation. And now people see that nowadays in many countries there is a levitating train. I will show you those things later. Now looking at considering the superconductor that you see here, you know that Faraday law. The Faraday law does not explain magnetic repulsion by superconductor. You see, look at the as I see you, it's this, if you hollow, the material is hollow, then you see, look at this, how magnetic field penetrates and the diverges. That means below its critical temperature, we call tissue, where the material below that temperature, the material behave as a superconductor, right? That means it does not allow the magnetic field to enter into it. That's basically known as Meissner effect. This known as, you see, so this is known as a Meissner effect. Look at these things. Now, Meissner effect associated with magnetization. Now, if material is not a superconductor, that means at any temperature, basically the T is greater than Tc, the transition temperature, then all the lines of force can penetrate. It's no more a superconductor because T is greater than Tc, and the lines of force, magnetic lines of force, can penetrate. Now, it happens to be a superconductor. Look at the lines of force. The material does not allow the lines of force, magnetic lines of force, to penetrate. So this is known as Meissner effect. That means inside the superconductor, B is equal to 0, the induction, magnetic induction that you see here, magnetic field, B is equal to 0, E is equal to 0. And there is a superficial screening current inducing a diamagnetic polarization. What is demagnetic polarization? That is equal to susceptibility, Chi is equal to M by H. Okay, so if this is perfect diamagnet, M by H is equal to -1. That means a superconductor behave as a perfect diamagnet. Because susceptibility is negative, if susceptibility happens to -1, this is perfect diamagnet. Okay, and the magnetic field that you see here penetrate with a exponential decaying in density. Strange thing that you see here. And I told you that magnetic field cannot penetrate the sample. Once again, I tell that, and look at the statement, magnetic field penetrate. How it's possible? Once I said that magnetic field, you look at the Meissner effect, magnetic cannot penetrate. Then this last statement I say that this be the penetration depth. What do you mean by that? That means there is some other materials which allows some magnetic field to penetrate. This will learn in the next slides. So this is the Faraday law of induction, because the +2 students are maybe much aware of those things. That means a change in magnetic flux will induce an EMF in the conductor. So there will be no induced EMF if the magnetic flux is constant with respect to time. So these are known as magnetic Faraday law of induction. So for our system, we do not have a magnetic flux, all this behavior. Now these things once again give you the flux. That's okay. When a superconductor is there, you put a magnet. That the lines of that you see, we call in the scientific term, we call flux, and known as the flux spinning. This is very important for the understanding of the other things we'll learn in the later slides. So this man you see here, this man is known as Kamerlingh-Onnes. Heck, Kamerlingh-Onnes. Okay, H.K. Onnes. Okay, right? And this man discovered superconductivity, a George physicist, discovered superconductivity in 1911. Okay, for the discovery of superconductivity in mercury, as you saw in the slides previously. And this man is known as a man of absolute zero. What do you mean that? Because this person spent his whole life in lowering, doing experiment of the different materials at low temperature. So people call him gentleman of absolute zero. And look at these things. This person who discovered superconductivity in 1911, he got Nobel Prize in 1913. 2 years after, he got the Nobel Prize. And you see that Nobel Prize can be obtained after 40, 30, 60 years also. But this man got Nobel Prize after 2 years. Even people got Nobel Prize after 1 year also. I will show that one. Now, superconductors have the ability to conduct electricity without loss of energy. This is a very important statement. Why? Because you call the resistance is not there, so there is no loss. Though there is no Joule's heating. Okay, when a current passes through a matter, there is a heating. We call Joule's heating, Joule's effect. Because superconductors do not have resistance, so they call there is no Joule's heating. This is very important things. That means, for example, in a copper, some energy loss when you pass some current. That is known as heating. Okay, but important thing that the copper that you use for conducting materials is not a superconductor. I'll show why it is not superconductor. But many insulators, which are bad insulators, they are superconductors. So these things, once again, for understanding, this is the transition temperature that you see here, the superconductor and non-superconductors. Okay. And this, because there is a phase change, as I mentioned initially, there is a phase transition. So TC is called a superconducting phase transition, a superconducting transition temperature. So that means you have a transition of a phase. What are the two phases? From a non-conducting normal phase to a superconducting phase. From a insulating phase to a superconducting phase. Right? From a non-superconducting state to a superconducting state. That is known as a phase transition. And you see here, this phase transition is very important phase transition. And you see that the normal state is basically a disorder state. And superconducting is a order state. So if you look at the entropy of a system, now the disordered high entropy and the ordered phase low entropy. Even if people which work on superconductivity, they have measure these magnetic properties also, like entropy, heat capacity, all those things. Because there is no scope, I can touch all these things because time manner parameters. So basically, you can have different phase transition. Looking at that, basically that is you can call it as structural phase transition. Even if there is all of the other phase transition also, look at these things, behavior of the superconducting material. Now, as I mentioned that perfect diamagnetism was marked by negative magnetic susceptibility, because we have mentioned that the susceptibility, perfect diamagnetic Chi is equal to 1. Now, what idea that we have all people knows that the material can be classified as different magnetic behavior. What will be diamagnetic, then paramagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic. Because you see, I have for simplicity, I give you that if the magnetic domains, right, they have a haphazard way of no arrangement, they are aligned in different direction. The total magnetic field, they oppose the change in the current, change in the magnetic field behavior, then the diamagnet. Similarly, paramagnet, you see, they are not completely ordered. Some of the things are giving a disorder on the middle of one. Now, if they have a complete order in one direction, these are ferromagnetic. If they are oppositely directed one by one up, one down, one up, one down, they are known as antiferromagnetic. If they are the magnitude is same, are not same, they are dissimilar, then you can call a ferrimagnetic material. So in this way, you can have a classification of those materials looking at their magnetic domain arrangement, or you can otherwise, if you have some knowledge, there is another electron spin arrangement. Then signs that you see here. Now, as I mentioned, superconductivity state can have 3 very important factors. One is known as critical temperature, the highest temperature at which superconductivity occurs in a material. Below this transition temperature T or Tc, the resistivity of the material is equal to 0. The second is known as critical magnetic field, SC, above which this externally applied magnetic field superconductor become a non-superconducting. Similarly, current also there, you do a critical current. That means you can have 3 important things: critical temperature, critical magnetic field, critical current. That means this is the maximum value of critical current for unit cross-section of this area that superconductor can carry without resistance. So these are the 3 important parameters that deals with the superconductivity. That means you can control this behavior of superconductor, or you can, the superconductivity can be destroyed by increasing temperature, by increasing magnetic field, by increasing current, right? So that these are the 3 important parameters that can control the behavior of superconductor. These things you see here, these 3 parameters are see here, JC, TC, and the SC. You look at those things, all right? That means these phase diagrams show that behavior of the change of field. TC with JC, TC with SC, JC with SC, and also TC with JC. These are the behavior of the superconductors depending upon these values. So for that, see things, the thin material I have mentioned here, one is known as the niobium titanium alloys, right? Look at these things. then niobium tin, niobium germanium. These are basically are known as alloys, right? Okay. Similarly, you can have element also. Like you can have niobium, you can have titanium, you can have germanium. These metals can be superconductor. But this type of behavior of two materials is known as alloys. Okay, that means a metal semiconductor, all those things combination there, they can be superconductor. But looking at the behavior, different metal have different phase diagram. Looking at the TC, JC, SC, you look at this the decay behavior, you can exponential behavior of these three parameter of the superconductor. Now, what you see here, I will give a brief history, not very lightly. I will not go detail of those things. A brief review of those things. This actually this history that initially, as I mentioned, in 1908, the Kamerlingh owns, while working at low temperature of liquid helium, which boiling point is 4.2 K. That means it can work as a liquid helium. I'll show you that detail of those things below next slide. Then in 1911, Kamerlingh owns that you see here, who got Nobel Prize in Physics for discovery of superconductivity, he found that mercury shows this 4 point below this transition temperature. The mercury shows superconducting transition temperature. In 1914, then see that once again as a find out a current experiment. What do you mean persistent current? That means if a resistance is equal to 0 and the resistance is very low, 10 to the maybe 10 to the power minus 10 minus 15 ohm. Now, if this in this condition, you can pass a little current. That current will not decay. It will flow years together. That current is known as persistent current, right? And the Meissner effect that you see here, which you call this the Meissner effect, we call it Meissner ocean field. Another scientist in 1933. In 1935, as Lolaton was saying that the London theory, that two brothers, H. London and F. London, they proposed the London theory. This is known as Friese and London theory. In 1935, basically give you the equation said that how this, looking at the Meissner effect, you can have a equation like the Maxwell equation, you can find out the London equation. Then another thing is the magnetic properties of the material has been identified, has been described, has been studied by two important theory. Sorry, one important theory which is known as GL theory, which people call it as Ginzburg-Landau theory. This is a very important theory. Okay, in 1957, this mechanism of superconductivity has been proposed by three scientists, Baden, Cooper, and Schiffer, who proposed this mechanism of superconductivity, we known as BCS theory, according to the three scientists, BCS. Okay, and these people who discovered this BCS theory in 57, they got Nobel Prize in 72. Coming to the second one, the aspect that we call Josephson effect. That means the superconductor junction, they can form a junction. Like you know, metal can have a junction, metal semiconductor junction, semiconductor junction. Similarly, superconductor junction, superconductor has a junction. This type of junction is studied by Josephson, which is known as Josephson junction or Josephson effect, right? And in 67, observation flux tube in type 2 superconductors. I have not discussed those things. The superconductor can have a type 1 and type 2 behavior. I will look at those things in maybe next slide. Right? In 80, the first accelerator, because this superconducting material can be used for superconducting magnet, because these are known as high TC magnet or superconducting magnets. Now, what do you mean by what do you mean superconductor magnet? If you can have a wire of superconductors, then you can have large magnetic field. If your copper wire can give you maximum of 1.52 Tesla, right? 1 Tesla is 10 kilohertz. This can give you high magnetic field of the order of 150, 170, like this order of Tesla field. So high field you can generate by use of superconducting magnets, right? And this things that this is the turning point of a new era. If time permit, I will give a flavor of those things. This is a fast observation of ceramic superconductor. That means your metallic elementally alloys which show superconductor
even people can show that ceramic many oxides, they can have superconductivity. This is known as high T superconductor. This to be proposed by Bednorch and Muller. I'll show you the next slide. And the people who discovered high T superconductors, tissue above 35K, these people got Nobel Prize the next year, 1987. In 1987 itself, the ceramic superconductor are tissue of 92K. You look at those things. These are known as high T superconductors. What is the beauty of the things? That the superconductor is above the liquid nitrogen. All these superconductors that you see below 35K, the liquid helium is used, right? But now you can use this liquid nitrogen, which is plentifully available in nature. You can produce also. Now that liquid can be used for material to use as a superconductor. That means if material is TC is 92K, then if you dip it in liquid nitrogen, that becomes superconductor. Simple. That's okay, fine. Then in 2003, discovery of metallic compound, another class of MgB2, okay, magnesium diboride, whose transition temperature is equal to 39K. This is 2 types of classical superconductors. So these are different way of preparing. Now in 2018, 2020, many people are working on look at things. And I will give you one slide that in this year, 1917 or 2017-18, then people have tried to achieve a superconductor which can behave as superconductor at room temperature. That is the beauty of the system. Okay. So now people are trying to this. There is no success. Still, there is experiment. Coming to next slide that you see here. As I know, the conventional superconductor has a TC less than 25K. We can have this is related to the elemental superconductor alloys. In 1986, they have the high T superconductor. So this liquid helium now can be changed to liquid nitrogen. This is beauty of the system. Look at the rounded this curve that see. These are basically elemental superconductor. Up to this 1986, this is this niobium germanium has a transition 23.2K, less than 25K. This is the system that you see here, where we use the liquid helium as a coolant. Now you can use liquid nitrogen coolant because this is more than 77K. This is the system that you see here. So that you see here, I will be not give justice to this talk if I do not talk about liquids. Now there is a super conductivity, there is also super fluid also. Two systems that you see here, the helium, the isotope of helium. One is a helium-4 and another helium-3. Helium-4 liquid that you see here has a boiling point of 4.23K, right? Helium-3, this isotope of helium, has a boiling point of 3.19K compared to helium-4 that is 1.423K. And the critical point that you see here, helium-3 is also lower of 3.35K compared to the helium-4, which has critical point is 5.2K. Okay, what beauty of this system you see here, that helium-3 has a look at I give you only simple relation those the helium-3 and helium-4. Helium-3 has less than half the density of helium-4 when it at its boiling point. Okay, and helium-4 is a boson. Look at those things. Though they are isotope, helium-4 is a boson, helium-3 a fermion. You know these things, what basically bosons and fermion. I will give you the, when I'll talk up those things, but boson I'll give some light also. That means bosons which obey Bose-Einstein statistics. Bose-Einstein statistics, Bose, our Indian scientist, okay? S.N. Bose and Einstein, because both the people, and there's according to name of Bose, this particle known as boson, right? And this thing that this helium-4 having 6 nuclear obeys Bose-Einstein statistics. Helium-3 has a 5 nuclear. Okay, looking at the spin arrangement 5, it is a fermion, obeying Fermi-Dirac statistics. So these are things that you see here. So now let us give some more detail of the fermion. Sorry, this boson, that is basically helium-4. Look at the phase diagram of helium. We will shift to superconductivity because I will stop this bosonic behavior here. And this is known as the phase diagram of helium-4, right? Look at this picture. That see helium-4 I can have has a transition, right? Boiling point is 4.2 K, but it has a transition of quantum fluid transition. We call 2.17 K. Okay, look at this point. This is known as lambda line. The line that see lambda line, the temperature known as T lambda. Okay, you look at a lambda, look at the English language lambda. This is lambda line. That see here, helium 1, I can call helium 4 that you see here. I can call it helium 1, helium 2 because helium 1 is a normal liquid like this we call as helium liquid. Now, if you cool further, this at 2 point below this 2.17 K, it's become helium 2, and now this normal liquid become a super fluid, which is basically known as quantum liquid. That's okay. That's a quantum behavior. That's what do you mean by that? That helium 2 here, it does not behave as helium 1. It has completely a quantum behavior. That means it's a normal fluid, it's a quantum fluid, right? And helium 2, as you see here, is a fluid we call superfluid. Does not obey the properties of classical fluid. It has quantum behavior. It come out of the container by siphon effect. What do you mean that? That once it become a helium 2, you cannot put into a container. You cannot put in a container. That means there is a siphon effect. Look at these things. These things I have drawn. Now look at, if you put some helium liquid in a container, if you are able to put it, right? And deep inside this liquid, the liquid which are inside this, they come out these things. Or if level is less, it's go into fill it till it becomes same level. Look at this thing. If level is high, this liquid come out of the container, right? This happen by a process we call known as siphon effect. Same thing also happens. Suppose you fill up to here and lift above this liquid, then liquid which are inside the container, they come out dropwise. Basically in the wall, they form a siphon. Okay, a capillary tube of the order of some nanometer capillary tube. So this liquid come out of this. This is the beauty of the system, which has known as superfluid. I will stop here. We will go to superconductivity. Now, once again discussing these things, people that you see here, BCS theory proposed by Baden, Cooper, and Schipper, and we call BCS theory explain the superconductivity at temperature close to absolute zero. Cooper realized that atomic lattice vibration were responsible for unifying the entire current that you see here. Another things come into lattice vibration. Nowhere we have discussed those things. Now remember, we will discuss the lattice vibration. That means they forced the electron to pair up into teams that could pass all the obstacles which causes resistance in this conductor. That means when the matter becomes a superconductor, the electron will no more be electron. That means this electron, some of the electron will convert to electron pair, which is called known as Cooper pair. I will discuss what basically Cooper pair is. That means electron will form a pair. Looking at this discussion that you see here, one can imagine a metal as a lattice of positive ions. These things we have discussed very beginning, which can move as if attached by stiff spring. We call basically in a language, we call harmonic oscillator. Single electrons moving through the lattice constitute an electric, and this is our fundamental idea that electron current constitute the current. We call the charge carriers. Normally, the electrons repel each other and are scattered by lattice, creating resistance. This is basically known as scattering process. Because electrons are negative charge, they repel each other. This is very understanding. What you see here, now we are discussing the motion of the electron in a crystal, in a lattice. Okay, that means when this two electron moves in a system, how they form pair, we call Cooper pair. Now, the two electrons that appears to team up in accordance with the theory of a BCS theory, right? that we see that both though they have negative charge, okay, and they should normally repel each other. Below the superconducting transition temperature, paired electrons form a condensate. Try to remember those things. Now, this Cooper pair start formation at a particular temperature. Now, if you go to very low temperature, another phase occurs, which we can call a macroscopically occupied single quantum states, because these are bosons. And the beauty of the bosons, all the bosons can occupy a single quantum state. So this is the beauty of the bosons. But fermion cannot do, because they have to obey Pauli exclusion principle, because two electrons cannot be the same state of the same spin or behavior. Which basically, if we have they have team up, they form a pair, and they should move. When they form a Cooper pair, the resistance drops. So you see, look at this, the Cooper pair formation. When two electrons moves, when one electron moves, it disturbs the lattice side. One disturbs a positive ion core that you initially, they displace each other, so that a positive space charge is created. Naturally, when second electron comes, he will see the positive charge here. So naturally, it will be attracted. That means to form a pairing, the phonon plays a role. So we call that known as phonon mediated mechanism. Look at this thing. This is a basic thing, that this is the formation of when two electron moves in a system, they form a pair, we call Cooper pair. And this is mediated by phonons. For that, we will call phonon mediated Cooper pair. Now, this is the idea for Cooper pair. That means in the superconducting states, the electron form pairs, known as Cooper pairs. That's all. Now, coming to the other aspect that, as I mentioned, the things that below this transition temperature, you have the critical temperature, all those things we have seen previously. Now, this resistivity can have two parts. One is a phonon part, another interaction of this electron phonon. We call phonon interaction. You look at resistivity. Resistivity has a two part. One is independent of this impurity, right? This is impurity part. So this independent temperature. And this is impurity part, which is the phonon relation of those things. This is known as T5. So resistivity is known as rho 0 and plus T5. That means this is contribution of the electron phonon interaction. This is for impurity of the material. So this type of law, what you call as a Matheson's law, if you read it and find it, this type law, a resistivity has a two part, one temperature dependent part, another temperature independent part. This is known as Matheson's rule or Matheson law. These things we have already mentioned, that is the Masonry effect. And one thing, as I mentioned, that can be have two type of superconductor there. This one a type 2 1 superconductor, another type 2 superconductor. What is there? We can classify those things. Look at the behavior of this magnetic behavior phase diagram, that this B versus T, or you can call H versus T. So look at these things. You have two phase. That means the type 2 superconductor are there, which can allow more magnetic field to enter into it, right? So look at those things like type 1 superconductor. If T is greater than TC, B is greater than BC, J is greater than JC. So these are, see, the superconductivity disappears, right? Look at these things, type 2 superconductor. For BC1, actually it has two transition critical field. Not only B, it has one critical field B, but it has two, BC1 and BC2, but it has only one BC. That means it has two critical field. Two critical field means, look at these things, you can understand here better. Now, if we make a plot of M versus H, applied magnetic field and induced magnetization, this type of behavior you see, the first one see from the red, this is a behavior of type 1 superconductor. That means if we increase the applied field, at a particular field, it goes to 0. That means a superconductor is destroyed, right? We call SC, thermodynamic critical field. Now, if you use a type 2 superconductor, then not only it has an SC, it has SC1 and SC2. Try to understand these things. This is basically the behavior of a type 2 superconductor, right? Now, in a type 2 superconducting material, right, you have two critical fields. One is SU1, another SC2. Try to understand. Up to SC2, it's a superconductor. For up to SC1, type 1 is a superconductor. Beyond SC, it's no more superconductor. But for type 2 superconductor, still you have a critical behavior, or you can behave as a superconductor up to SC2. That means you have a state between SC1 and SC2, or you can call it also BC1 to BC2. All right, what do you mean by that? That means this state that you see, very important state of the matter. It is called as a mixed state. And you see, this is known as normal state. This is mixed state. This is your superconducting state. What do you mean by in the mixed state? Material also behave as superconductor. What is extra things that here? That means magnetic field can penetrate up to SC2. Beyond SC2, it's a normal matter. This is the crux of the problem, and the difference between type 1 and type 2 superconductor. Right? For typical 2 system, I have given you here. Suppose you take a material like Ti, aluminum, mercury, lead, elemental superconductor, they have Bc at 0K. These are the values of Bc in terms of Tesla. Take a type 2 superconductor like niobium. I have not taken the complex one. Simply, niobium is, though it is elemental, it's a type 2 superconductor because it allows a magnetic field to penetrate. So Bc1 is equal to this much, Bc2 is this much. You see how much it is. It is millitesla. This is also millitesla. But if you go to another class of material that we discussed, high T superconductor, whose transition is more than 35K, they have field, not milli, but Tesla. Right? So high field can penetrate. So this is the behavior of this superconductor we classify as type 1 and type 2 superconductors. Right? You see, so now you see this is a formation of Cooper pair as in BCS theory. This I have already discussed. And one theory there known as isotope effect. That TC, that means if we take an isotope like mercury have 2 isotopes. Okay. So that means if you have look at the behavior, look at the mass of the isotope, then TC is, if M is more, then TC is less. This is known as isotope effect. So looking at this behavior of these things, look at the isotopic effect, metal constitute. So naturally, one idea comes that phonon should play a role in superconductor. This is the idea of BCS theory. Why? Because looking at the behavior, they observed that if this is the situation, that phonon must play a role, right? So they form a pair we call Cooper pair, okay, and the creation of Cooper pair due to phonons. These things are already there, and we discuss those things. That means in a superconductor, the net effect of attraction, electron attraction through phonon with the mediator, with the mediator. That means electron Coulomb repulsion is attractive, and the Cooper pair become a singlet state with a 0 momentum and 0 spin, because these 2 electrons that you see here, if something is there, I can show you, they form a, just like movement is there. If it's not there, I think it is not there. Okay. So now they form a pair, we call Cooper pair, one spin up, another spin down. That means one momentum K, another momentum. I will see the next one I will show you. So this, I will skip this one. I will skip this one. So, let me show you, and I will come discuss all this. Now look at these things. That means also you can classify the superconductor in 2 ways also. That's type 1, type 2, depending upon 2 parameters. There we see that this penetration depth that you see here in this type 1 superconductor is very, very less, because the idea is that a small magnetic field destroys the superconducting behavior. Look at this here. Now, this like 2 parameters there. One is London penetration depth, we call that lambda L. Another is coherence length. What they are actually. Now, London penetration, these are 2 parameters once again I use for classification of type 1, type 2 superconductors. So now London penetration is the depth. You see, we call lambda L is the electron fold. That means electron decay by 1 by E. For that reason, we call E fold decay. That means once this matter inside this, the magnetic field enter the superconducting system, then this field decay like 1 by E. Okay. And we call this basically looking at the Mesmer effect because it has so partial Mesmer effect. And the magnetic field can penetrate to the order of the lambda L that you see of the order of 10 to 3 nanometer order. Coming to another parameter we call coherence length, J. This is the average size of Cooper pair in the superconductor with the range that varies from 10 to 100 nanometer. Look at these things, two things. And this is much larger than the interatomic lattice because lattice spacing or the interatomic distance is of the order of that is 1 angstrom to 3 angstrom or 0.1 to 0.3 nanometer. So this is the two parameters that has identified whether the matter is a type 1 or type 2 superconductor. Look at these things. Now we take a parameter where the ratio of this lambda L to J. This is coherent length, this is penetration depth. And this K will know kappa, basically known as Ginzburg-Landau parameter kappa. Now if the ratio is less than 1 by root 2, it's a type 1. If the ratio is greater than 1 by root 2, it's a type 2. What do you mean by that? Look at this behavior. That means if for type 2 superconductor, this is small. So naturally, this is large. So this is type 2 superconductor. Look at these things for consideration. You see different materials, indium, lead, tin, all those things somewhere there. Look at their behavior. Lambda L and this J, right? This is of the order of nanometer. Look at thing. Lambda L is equal to this for these materials 24, 336. Okay, 360 been very high. So naturally, this ratio, if you put it, it will be 1 by root 2. Now, for this type 2 superconductor, you make a ratio of those things. This is the behavior for type 1 system. Now, if you put type 2 superconductors, look at the behavior. Both these things are there. Okay, so that this is so that this ratio is very large. So naturally, this is known as type 1, type 2 superconductors. I think this is some of the behavior that you see here. For different material, you can see this the critical field of the second critical field, BC2 or SC2. Look at the behavior. If you BC2 versus you measure the temperature, these are the materials you see. If TC is more, then BC is equal to more. So these are three materials like 1, 2, 3, 4. How see how the transition temperature behavior changes with temperature and critical field, and this can have a relation that you can put it this way. And these are the things that the type 1, type 2 superconductor have different values. And one thing I want to make you understand that type 1 superconductors are known as soft superconductors and type 2 superconductors are known as hard superconductors because this type 2 material can allow superconducting magnetic field to penetrate. So these are some of these examples that you see here. This is known as this behavior of the type 1, type 2 superconductor. This is very understanding that you see here that when you have this type of arrangement is there, the electron pair you see in a conventional or low temperature superconductor, a type 1 superconductor, these are the, see that how they pair the length is from here to here. Now in the right hand side, electron pair in a cuprate superconductor, basically a high-tech superconductor, you see this, this coherence length is very short. If these are two electrons form a pair, the length is very short as compared to the type 1 superconductor. That means coherence length is very short, penetration is very large for type 2 superconductors. So these are the Feynman diagram that you see here. When the two electrons with different wave vector k and k prime, and this phonon has a wave vector q, they can have this annihilation and creation of this behavior, so that electron pair can be formed in the association with the phonon, so that this is known as electron phonon mediated Cooper pairs. These things are already there, that the critical field that you see here can be related by the relation where SC0 is the critical field at 0 Kelvin AC at any temperature, they can be related by a equation. That means if T and TC related those things, AC can be large. So this behavior is used for measuring the critical field of the superconducting sample. This is the energy gap. Don't worry about things. This is standard things. That energy gap appears like a semiconductor system. The energy gap appears a superconductor at the Fermi surface, right? That means energy gap is more than the gap energy. When the Cooper pair breaks down, that means if the energy is equal to E is equal to h in classical way. So then Cooper pair breaks. And remember this energy gap appears at this the Fermi surface as compared to other systems like these semiconductors. This is the things that I can give you some idea of this high temperature superconductor. Okay. What is high T superconductors? The high T superconductors are superconductor which the superconductor does not satisfy BCS theory. These are type 2 superconductor whose transition temperature is more than 35 K. That means the BCS theory fails here, right? If BCS theory fails for high temperature superconductors, the big theory.
ठीक समय सब दिन आसीबो हला कारण पिला मानकर भीड़ रहइबो कॉलेज रे त बुझी कहबो तुम दि जण आसीबो मो पागु उज्जवल साथ थिबे हम बस कथा हवा से एडजस्ट करबा कोन देह पा आगो ना कोन करबा हां
Okay, please mute your system. So now we are discussing this BCS theory because you see the BCS theory you have already discussed that the phonon mediated mechanism in high T superconductor BCS theory fails to explain. Now this experiment, the proposition, the theory, the models are there, right? And this high T superconductor has been discovered in 1986 by Bednarz and Muller. Two people are there whose transition temperature is 35 K and system is a ceramic. What ceramic looking at these things? It is nothing but lanthanum, barium, copper. These are the oxide form. Lanthanum oxide, barium oxide, copper oxide. 3 oxide mix in a stoichiometric proportion and TC is more than 35 K. I will show you. These are the people that you see here, two people, Muller and Bednarz. The two people that you see here, initially the upper, this figure is during their laboratory when they discovered it. Now recently, maybe 2-3 years back, this is the situation of the two people that these are the two stalwart of the discovery of high T superconductor. I happen to meet these two people. I met these people in a foreign country, the Muller, now in year of more than 90. Okay, and the Bednarz, this person, if anybody knows, this person came to India, Bednarz. So I met these two people, and they have beautifully explained. The Muller has beautifully explained the model of superconductivity. They are two people that discovered high T superconductors. So looking at these things, that high T superconductor initially proposed, discovered this by these two people, Muller and Bednarz, in 1986. These people got Nobel Prize in 1987. Not only this material that La2BAXU4 is there, but many materials are there. Okay, I have not discussed because this is a long history of those things. And that see why I mentioned, because you look at these things in 1987, another material, these are basically oxides, right? Yttrium oxide, barium oxide, copper oxide, right? These are the oxides were mixed together and they form a TC of 92 K, and people called it as YBCO, right? And why I am mentioning these things, because some of my students who got all those things research work, they work on this material, they prepare the material, measure the transition, and they are associated different properties. I will show some of these slides. These are the another material we call thallium based compound, which TC is of the order of 120 K, 122 K, was discovered in 1980. Another mercury based compound like mercury MaHg, we call it as HBCCO, like Hg, Ba2, Ca2, CO3O. This is oxygen content of the material. HO10 means this is oxygen, if you look at this, the charge state, the valence state of the metal, you can look at this thing, yttrium 3 plus, barium 2 plus, copper may be 2 plus 3 plus, oxygen is 2 minus. That means you can have a combination of anion and cation. Very fundamental thing also. When look at the once again, I come back to the another metal with this material that you see here, La2 minus X BaXuO4. Actually, you see this. I think I have one slide. I can show you that this the initial compound is La2 CuO4, and the La2 CuO4 is simply a material. It's an insulator. Now, if you put some of this lanthanum with some composition with the barium, barium was initially not there, 2 plus was not there. Lanthanum and copper was there, La2CuO4 was there. Now you put some of the barium, then you can create large number of holes in the system, because this is 3 plus, is 2 plus. So now you can create some holes, and this is the responsible of superconductivity. This is the beauty of the system. That means an insulator become a superconductor by some of the creating defects, by putting some of the impurity of a barium. So that you can see, as I maybe have the next slide, I'll show you this. These things I will may show in the different slides. Now, this is not the end of the story, as I mentioned previously. Now, this is the highest TC up to now, in the sense that this is this TC 134 K of this room temperature and normal pressure. Now, if you give some pressure, this material can be a superconductor up to 164 K. That is superconductivity, high T superconductor under pressure. I will come to next slide. I will show you. The recent development that you see here, looking at this maybe 1 year, 2 years back, this recent discovery of high temperature superconductor, the tissue may be the order of 100 something, 166 K is sulfur hydrides at a mega pressure. We call megabar pressure. Break the traditional belief that TC limit may be 40 or 100 something. For this conventional superconductor, this TC may be of the order of high temperature. Because we are trying, people are trying to have a superconductor which can attain transition at of the order of room temperature. So that you call room temperature superconductor. Now, if this is so, then this will open up doors in searching new high temperature superconductor in compound made of light element. Because you see, nothing is there. Sulfur and hydrides, hydrogen and sulfur, nothing is there. Look at those things. Now, 3 stable and metallic species with the stoichiometries of this sum, HSC2, HSC, and S3SC. Nothing is there. You see it, only 2 elements, selenium and hydrogen, right? You can call hydrogen rich, which give this TC of the order of 200, maybe more than that thing. We call it if TC of 204. We are going to reach a TC of the order of room temperature. Which system? H2S and H, hydrogen sulfide and rich hydrogen. At a pressure of 200, this mega, right? Giga. Now it's a mega Pascal. Now it's gigapascal. If you give high pressure, then transition temperature can be reached of 204 K. This is the this report, the scientific report that you see here in 2014, right? So these are things that people are striving very passionately strives to have room temperature superconductor. What I mentioned, you think that nature is full of surprise, and from the present scientific knowledge of superconductivity, it is not impossible that superconductivity at room temperature or above might realize one day, which is called as room temperature superconductors. An electric current that flows forever without losing any energy means transport of electric power with virtually no loss in the transmission cable. Try to understand. Now you see, we are generating power at hydropower station or a thermal power station, maybe at your Konya or Onugul and maybe Hirakud, but reaching you maybe nearly 70% is a loss on transition. in the process of transmission. Okay, so that see if the transmission loss is not there, whatever produced at the center, that can reach at your place. So that means a revolution would also happen. If the development of superconducting magnets, we call levitation, we call superconducting maglev trains as a transport system in the future. Not in the future, also it is possible, and India also to have this run this bullet train, right? The maglev train also, India also planning. This is also successful in Korea, South Korea, Japan, China, and some other European countries. This maglev train also in speed, which runs more than 500 km per hour, right? This is known as maglev trains. Although room temperature superconductivity is still a dream, many scientists believe that one day it will be realized. This would unleash astonishing novel technology, alter our daily life tremendously, naturally. Like the transistor, the solid state transistor development. Now, if you remember a small information, in around 1971-72, some of you are the teacher that you are in this seminar, they have heard, they might have seen that computer in Utkal University has occupied a big room, right? That is known as computer that time, 1130 computer. Okay, now you see the computer, you are using computer and many people are using computer. That computer PC that you are using, the laptop you are using, how much small is there? The energy, this memory has increased tremendously. This could possible only the development of transistor, the FET, okay, MOSFET, okay, CMOSFET, all those things, these memory chips. So I think that if someday this you can have this transmission loss power, then your daily life will change tremendously. So I saw a figure here. As I mentioned, that BCO's theory proposed the mechanism of low T superconductors. Now this picture shows that for high T superconductor, no mechanism have been proposed. That means people are trying to identify different theory and model. I'll show you. Now this is the 6 or 7 the blind people try to identify, because these people are blind, they cannot see the elephant. They also know feeling of how the elephant look like. So now the 7 people or 6 people what you see here, just like 7 theories to propose high T superconductor, these 6 people go, the blind people, they go and touch different part of this elephant and they propose this size of the elephant. So naturally, which touches the leg, his observation will be the elephant like a pillar. If who touches his tail, he said that is just like a rope. The people who will touch the tongues, his throat, his ear, then they propose differently. Just like a rope, just like a pillar, just like anything else. So that means this is the things. Now people are working with different ideas, different models for propose the mechanism of high T superconductor, because BCS theory cannot give this explanation for the mechanism. For to propose the mechanism, people are working with different theories, different model, different experiment like photo emission experiment, transport experiment, then theory like Newton scattering, tunneling experiment, STM, scanning tunneling experiment, defects. So defect is important things. I'll show you some slides maybe. Then pairing of mechanism, ultrasonic behavior. That means this is the different theories, manifold prediction is going on to identify this mechanism of high T superconductor. It is also understood that the mechanism of high T superconductor is proposed, the next time he will get the Nobel Prize. So this is the work going on in worldwide. Now we have learned this superconductivity that's here, give you some application of superconductors for the benefit of society. Now what are the high T superconductors that you see? Electrons in electronic atmosphere, electronic system, sensors, supercomputers, cryo-electronic components, in medical techniques, SQUID, magneto-resonance imaging, MRI, then power engineering, generator, motors, transformer, current limiters, switches, cables, energy storage. I will show you next slide. Basic research can be going on. High field magnets, SQUID sensor, bolometers, particle detectors like superconducting magnets can be used. Please tell me where I can stop. Okay. Then microwave techniques, filters, antenna, resonators, delay lines, active components. Even in traffic engineering, you can have magnetic transport system, ships, engines, maglev trains. So these are the different ways that superconducting magnets or these maybe basic type of magnets or superconducting system has been used now in different aspects of our applications in social life. These things already there. This is not imaginary things. The first one is known as these things that you are already seen, or some people might have seen. This is known as MRI, the scanning system, magnetic resonance MRI. This is scanning of the brain, the scanning of the body of the system. This is used in every part of this country. This is known as MRI. The right hand side is known as NMR, nuclear magnetic resonance. So this has been used by different research purpose to know the magnetic quadruple behavior. The left hand side of these things is a train that you see known as this levitating train or maglev. This is also in operation. And this thing that the right hand, the bottom panel is known as a SOI formula, because in Keike, Japan, you might have heard this. They use the superconducting magnets. Niobium, titanium, niobium, germanium, this type of materials that use in magnet. That means thousands of superconducting magnets are used in this formula, which basically known as LHC laboratory. This is also the another thing that high temperature superconducting power cable, power transmission cables are there. Look at these things that you see here. This high TC material that you see here are ordinary cables here. Now you can prepare now the cables, right? And you see this cable can carry more than 150 times the electrical as compared to your copper wires. This is another transmission cable that is prepared for this transmission of useful for electrical applications. Now, if you give time, I can give this. What are the research we are doing here? So, please tell me where I can stop. I cannot should not bore you.
Yes, sir. Yes.
Now tell me when I can stop.
Sir, now.
No. We see, I have some slides
yes.
so that these are this current work that some of my students.
Yes, sir. Yes, sir.
So,
yes, sir. We'll do.
So if you do not bore me, tell me what at what time I should stop. Don't worry about those things.
Sir.
Is it okay that with all of you?
Sir, okay,
Yes,
okay,
sir.
sir. Okay.
Okay, fine. Now
Yes,
look
sir.
at these things. This is the study that we are doing our NIT. Some of the system, in your system, we are different aspect of there, but we are looking at the critical current aspect of material. Our student prepare this YBCO high T superconductor. We call YBCO or Y123. And these are some of the students that already 3 are completed their PhD. 1 is working in the aspect of superconductive. Other people are working in the magnetic system. These are only the 4 people are working. They have completed, 3 are completed. 1 is Vivek is working, and he has to submit recently. These are the work we concentrate with critical current density. And these are the things that you see. Don't worry about it. I try to make you some of the flavor that this is a YBCO superconductor. In a pure YBCO superconductor, these are the resistivity curve. That means you can plot resistivity versus temperature. And this is the transition. That means this material shows transition of the order of 92 K. My students are preparing this material, and what they have, they measure the critical current density. And the TC of the material can be measured from the derivative of the curve. They can give you a peak, and that peak show that what is the transition temperature of the material. That means they measure the transition temperature of the material, which is more than 92 K. But our aim is not measuring TC, because this is a well-known thing. What they did, they have YBCO, a superconducting material. In YBCO, they add some CNT, carbon nanotube, in different concentration. That means they want to create some defects. Okay. Now, if defects are there, what happens? That in the process, they want to create some type of defect in some nano defects. So these defects can be created by putting some non-superconducting material, creating non-superconducting phases. They can create that the crystalline defects, or they can make defect by process of irradiation. What do you mean irradiation? They can create nano defects. That means original material, they want to make some defect inside the material by this process. Okay, by putting some elements of materials, ions, whatever may be, or they can, I can show only, if you time permits, I can show you only this irradiation aspect. That means this sample, the superconducting sample, the thin film sample, has been irradiated with heavy ions, with high energy particles. Like in Delhi, one center is there known as University Accelerator Center. It is used for all the university people. They can propose and they can work there. This is free of cost. This is DST center. So if anybody wants, they can use this facility for their research purpose. And we make irradiation of our sample to create nano defects in the material. Okay. Now what you see here, this by creating nano defect, we want to increase the critical current density of material. Now, for the beauty of this system, you see, if we make this material a nano materials at nanoscale, which people call it a size dependent properties, the different properties, you make the particle size as nano, reduce order, what are the property changes? The chemical property changes, so reactivity, catalysis, thermal property change, melting temperature, mechanical property like adhesion, capillary forces, optical properties, absorption and scattering of light, electrical properties, tunneling current, magnetic properties, supermagnetic effect. But that's okay. Now, what we did, this is the effect of size dependent. Naturally, what we did, we want to put some nano in your system. And the defect that you see here, very fundamental thing that our plastic students are learning, the different defects are there. That means we call these defects are like point defects, extended defects, vacancy, interstitial defects, substitutional defects. That means you know these defects. That means you can create defects. The point defects are called imperfections, such as vacancy that are located typically at one, in some cases a few sites in the crystal. You can create also defect, that means defect that involve several atom ion and occur over a finite volume of the crystalline matter. These can be called dislocation or stacking faults. Similarly, you can create a vacancy. What do vacancy? An atom or ion missing from its regular crystallite site. That's a vacancy. What is interstitial? Because these things are see here. Look at these things that you see here. That means you can create a vacant site. This is known as A is a vacancy. This is a ion go to interstitial site. This is go to the lattice site. We call as substitution, a small substitution. This D is a large substitution because you see as compared to a lattice ion size, you put a larger ion. So this is known as substitutional defect of large ion. This is known as Frankel defect. Look at these things. You put these things, a defect at the here, okay, and a vacant here. This is a Frankel defect, and this type of defect is known as Scotty defect. That means a position is vacant here. Looking at things that already here, you can make it this. If a material is there, you can create a vacancy. You can create a substitution. You can have a boundary at this junction. We call grain boundary. Okay. You can have a fault like this, you know, stacking fault. You can make a twin boundary in between here. You can have a dislocation like this. So in this way, you can create defect in the material, your material. What is defect? This is plastic defect, dislocation is there. So what do you mean by these things? That means why nanomaterials, polycrystal materials are unstable? Because these are unstable because you create some defect inside the system. Now, if you anything?
Battery sir down there.
Hello?
Sir,
Hello?
battery discharge some participants.
Oh, acha. Okay. Okay then. No, I will don't take much time. I will complete maybe 5 to 10 minutes. So yes, now sir, you see, now if you create artificial defects, now this is actually we call we create defects, now called defect engineering. That means defects are necessary for material for useful purpose. You see that defect, we call defect engineering a versatile tool for tuning the properties of materials. We call defect engineering a path toward exceeding perfectness or perfection. So this thing that knowingly you create some nano defects, right? As I mentioned, I will touch upon not other things because my students are working with different nanometal introduction to their system. But this is very fundamental thing that you can create different types of defects. We call artificial pinning centers or defects, like 1D artificial centers, 2D artificial centers, 3D artificial centers. What do you mean that? That means if you have if you make ion irradiation, they have linear defects. These are known as one-dimensional. If you have a thin film, you can have two-dimensional defects. You can, in the ball system, you can put some nanoparticle. These are known three types defects, three-dimensional defects. So that means you can create what my students are doing. They put some amount of this material like things they have in bulk system, right? They have create three-dimensional defects. Now, if you make the two type thin film, because they can have defect in the boundary and surface. That means if you have linear columns, there is no one-dimensional defect. So these are so how can create artificial pinning centers. This is the mechanism. So that means I will short my talk. That means if you have a system, if ion comes here, then these are different process that occurs by the process of we call basic ion solid interaction process, like nuclear process, electron process, and so many processes are there. You can electrons come out, you can X-ray can come out, you can have recoil of the electron, all those things are there. Something that you see here when projectile comes with high energy, that you see it goes depending on energy of the particle, we call projectile. If it goes high energy, it can pass through. If it's some energy less and the depth is more, the ion goes and sit here. We can note ion implantation. This is also used by different people in semiconductor technology. So this way you can have different the process that involve for the ion irradiation. So this thing what you did, we have a YBCO superconducting sample, prepared a thin film on the substrate, and these are irradiated by 200 mega electron volt. You see high energy. Mega electron of silver ion irradiated on epitaxial thin film, and in the process we create defects. You see, if there is a centimeter of these things, we only create some nano order defect, and these nano orders can be used for this enhancing critical current density. So these are the effect of nanoparticles in nanomaterials. And what you see, we only measure the critical current density by this model, by measuring this the change of the magnetization by the squid. This vibrating sample magnetometer, magnetic measurement, we measure what is change in magnetization. Look at these things. So this is, don't worry about things. This is an experiment where the sample under the squid or this VSM give you this type of behavior. We change this delta M by this upper C to below here. This time is known as delta M. We know the sample dimension, and then we measure the critical current density. So if you measure the critical current density, time dependent critical current density, you see the critical current density increases by creating nano defects in your metal. That means you can create the critical current density of the metal by creating nano defects. These are different materials, that's all. That means you can create this material, the different materials, by creating ion irradiation. This is beautiful thing that you see here. The critical current density can be measured with different field, different temperature, and so that we have encouraged the critical, not only we can measure the critical current density, we can also the pinning force. Look at the pinning force, you enhance the pinning force in this material. These are same thing also another material with different fluence, different energy, we observe the critical current density. Also, we can measure this SC2, the highest, this critical field that your material can have, we can measure from the same experiment. So in the conclusion, we can say that defect is necessary to crystal material or metal to tune advantage to the properties of the material, reduce the size of the particle to nano order, you can modify the properties of the material. Although room temperature superconductivity is still a dream, many scientists believe that one day we will have realized this one. This would alter our daily life tremendously. The successful prediction, proposition of this mechanism of high T will bring Nobel Prize in physics immediately. High T superconducting material could enormously give a promise for a variety of different applications because of this ability to transmit a current without any dissipation at relatively high temperature. I think I should stop here. This is another story of this thing because that Nobel Prize in superconductivity has up to now, 2003, it has 10 Nobel Prize in superconductivity, starting from 1972. In 57 BCS theory, these are the people that who got Nobel Prize in 1972. Okay, in 87 2003. And this is a story that who got Nobel Prize, who the first people who got Nobel Prize. This is the Ranjan and Shibiram are the first Asian who got the Nobel Prize in physics. Okay, so these are the theory and experiment. Are they mutually exclusive? No. Both people working in theory and experiment, they got Nobel Prize. Even if the people who got Nobel Prize like this John Baden, he got Nobel Prize both in theory and experiment. Even if people got more than one Nobel Prize, like you know Marie Curie and all the Curies, scientists who received 2 Nobel Prizes in chemistry, Frederick and Sanger. Then science and social science, are they different? No, people have got Nobel Prize also in physics. Sorry, Nobel Prize in science also. Peace Prize also. You see that scientists who got Nobel Prize in peace, our scientist Linus Pauling, we know Pauling got Nobel Prize. Similarly, you can see that the science, engineering, and medicine, are they different? No, they can have the science, engineering, medicine, they can have got Nobel Prize. You can see here. Even if the people see got Nobel Prize in physiology, the Becke, that's a G.V. Becke, he got Nobel Prize in medicine. Similarly, these things happen. Those things, many people that the outer part Nobel Prize up to 30 years of which things got Nobel Prize in psychology, physiology and medicine. Even if father and son the Nobel Prize, that means Henry Bragg and William Bragg, both father and son got Nobel Prize. Even if father son, they have no relation. That means father J.G. Thomson and G.P. Thomson, father and daughter got Nobel Prize. Curie and Marie Curie and Erin Juliet Curie, both father and daughter Nobel Prize. Uncle and nephew, you know, Indians, C.V. Raman and Subraman Chandrasekhar. Wife and husband, Juliet Curie and this Erin Juliet Curie, wife, husband. Even if Perry and Mary, brother-in-laws, the Charles Dorin and Salo, they got this relation is brother and brother-in-law. I think I have completed this, whatever things I find for you. Thank you for your attention.
Thank you, sir.
Thank you, sir. I request participants. I request the participants.
Sir, there is...
Tell me.
Please unmute yourself, Lalatendu.
Unmute Lalatendu.
Okay. Yes, sir. Hello. Sir, some questions are there.
Okay, fine.
Why 2 electrons are only responsible for Cooper pair? Why not 3 or 4?
You see, pairing is formed. This is basically 3, 4. The idea is different. One thing that 3, 4, 5, 6, I do not know, because basically understanding that 2 electron pair we call Cooper pair. Okay, this is the things that is observed. Why not other electron can combine with those things? Because you see, these are a bosonic system. When 2 electrons form a system, we call Cooper pair because one spin up, another spin down. This is when they move together, right? And in presence of the things that why 3 electrons, 4 electrons do not combine, I do not have an idea of those things. Because it is found that 2 electron form pair is Cooper pair.
Yes, sir. Okay, sir.
Any question? Request.
Ah.
I request Mr. Pradeep Kumar Sakti, senior lecturer of our department, to deliver.
Okay, okay then, fine.
I deem it a privilege to extend vote of thanks to all of you on the webinar of the Department of Physics, SG College, Konikapada. I am very much obliged and extend our immense gratitude to our beloved principal, Professor Daitar Raut. We are very much proud to have an eminent scholar, a dynamic personality, and profound knowledge in physics, Professor Dr. Dhruvananda Behera, HOD, Physics and Astronomy, NIT Raurkela, the chief guest of webinar. We are very much obliged before him as he spent his valuable time for us. So we extend our thanks to him on behalf of department as well as the college. Moreover, we are very much thankful to HOD, organizing committee, participants, students, and employees of the college. Thanking you all.
Thanks all. This is the end of the webinar.
Okay, thank you all.
Sir.
Yes, sir.
Okay, okay then, fine. Okay, Lord, tu kinti kona besh samay higala ki?
sir. Nice, sir. ठीक
ଅଛି. Okay.
Aଜ୍ଞା sir. ବଢିଆ ହେଇଛି sir.
Okay, fine.
Thank you so much, sir.
Okay, fine, fine. Thank you. Thanks a lot.
You can leave now.
We can leave now.
Yes, sir.
Participants, we have uploaded the feedback form link in the chat box. You can fill the form and get your e-certificate, which will be sent to the spam folder of your Gmail. And after filling the feedback form, please check your spam folder. Your certificate will be there. Thank you.